So the another application for TIR we are going to study in today's class, that is optical fiber. Very important application. Many questions have been asked in NEET and JEE as well. Optical fiber. So what is optical fiber? It is nothing. It is just a device or just an instrument or to transfer the information in form of the light signal. Okay, device to transfer the information in terms of in form of the light signal. In form of light signal, right? What is its construction, or what are the conditions for optical fiber to work, that we are going to study in detail. So this, firstly you must know that this optical fiber is basically made up of two materials. It is in the form of a tube, and in this tube is also is made up of two materials like that. Now in this tube, this outer material, this material is called cladding, and this inner material, that material is called core. And what is there, that this refractive index of core, if I will write N of core, is kept greater than N of cladding. Why it is kept greater than, you will come to know in the upcoming part, in the next part of the video. Okay. So what will happen, that if you will incident a light ray into this core at some angle of incidence, let me write it as theta naught. Got it? So what will happen? Of course, this core's refractive index is more than cladding, but it is greater than. So it will of course be greater than the refractive index of here. So what will happen, that this will bend slowly, slightly towards the normal, like that, and then it is again incident onto this cladding. Okay. So what will happen, that again refraction should happen at this boundary. So for this specific refraction case, this light ray is of course traveling from denser media to rarer media, right? And if it is traveling from denser media to rarer media, what are the chances? What may happen here? Yes, if a light ray is incident from denser to rarer media, that is the condition for total internal reflection. We have already studied in the last videos, right? Now, but another condition also has to fulfill for this TIR to happen, that if this angle of incidence is I, that means for TIR to happen at this boundary, what is the condition? That this I should be greater than IC, of course. If this I become greater than IC, what will happen? This light ray will be totally internally reflected, and you can again see that this is a vertical, then this angle will also be equal to the angle of incidence I, according to the laws of reflection. Then this angle, you can see it is what? Alternate interior angle. It will also become I, then it will again undergo TIR, then it will again undergo TIR. So it will keep undergoing TIR until and unless it become out of this optical fiber. Got it? So now you can see easily that this light ray which is entered from one end is emerging through the another end. So why can't we use mirror in this case? We can use mirror also, na? Like that. We can use two parallel mirrors, and what will happen? This light ray will undergo multiple reflections and information is transferred again. Why we are taking use of TIR? So in TIR, I have told you already that in the TIR, this TIR is 90%, not 90%, even more than 90%, is efficient more than 90%. Okay, or its efficiency is more than 90%. That means, what does that mean? That if any information is incident or any light ray is incident, then the intensity of this light ray or the energy contained in this light ray will be reflected. 90% of its energy will be reflected, more than 90%. Approximately, it is given in some books as 98%. Somewhere they have given it that 95%. So what will happen, that 90% of its energy will be reflected instead of being absorbed, or instead of any refraction. In this reflection, what will happen? In this reflection, some part of this energy is reflected, some part is absorbed, and some part is refracted also, like that. So using TIR, firstly, cancel out any chance of the refraction. Why? Because all the light is totally internally reflected, because all the energy is incident at an angle greater than critical angle. So there is zero chances of refraction. There are zero chances of refraction. Instead of refraction, what will happen? Reflection will happen. So this first thing, we diminished or we cancelled out the chances of this refraction. So the energy which can be lost through refraction in case of mirrors, it is, we have saved that energy. Okay, we have cancelled out that risk. Got it? So that's why we are using TIR. So it is 98% of the energy is transferred, is reflected. So that's why we are using TIR instead of the multiple reflection. Got it? Now, what are the conditions for this TIR to happen? Now you can see one condition is only, because making this core more denser than the cladding, we have made sure we have fulfilled the one condition for TIR. But another condition, I has to be greater than IC. We also have to fulfill again. So for that, what we should do, can you tell me that if this angle is theta naught and this angle is I, can you tell me, if I will zoom this out, can you tell me what is this particular angle? So for another conditions to be fulfilled, this I should be greater than IC, and this I of course is depending on this theta naught. So let's calculate the value of theta naught for which I will always be greater than IC, right? So for that, you can see that this angle is of course 90, the normal which is making with the axis of this optical fiber is 90 degree. Then this angle will of course will become how much? Can you tell me? This angle will become of course 90 minus I, right? Got it? Now, what is the relation between this 90 minus I and this theta naught? Let me consider that refractive index for the air is, let's say N1 is the refractive index for air, and N2 is the refractive index for core, and let me write that N3 is the refractive index for the cladding, right? Now, if I will write the Snell's law for the first refraction which is happening at the boundary of air and this core, then I can write that the refractive index of air and 1 into angle formed in this air, that is sine theta naught, equal to the refractive index of this core and 2 into angle formed in that medium. This angle is nothing but sine 90 minus I, right? Got it? So I can write that sine theta naught is equals to n2 sine 90 minus theta is cos theta. So it will become cos I divided by n1. That is the first, that is the expression we got. Next, now can you tell me, if I will increase the I angle, or let me write, if I will increase theta naught, if theta naught is increased, what will happen to this angle? This angle 90 minus I. Let me write this angle as in as another symbol as r. So r is equals to 90 minus I. So if theta naught is increasing, can you tell me r equal to 90 minus I? What will happen to this angle? If angle of incidence is increased according to Snell's law, what will happen to this angle of refraction? That also increases, right? And if it is increasing, 90 minus I is increasing, that will mean what? This I is decreasing. Got it? Or if you can't understand it, let's take it reverse. If this I increased, if this I is increased, what will happen? This 90 minus I will decrease. Sorry, this theta naught should also decrease. So from this case also, that means for I to be greater than IC, to be greater than a particular value, to be greater than IC, that means this I should have some minimum value. That means it can't decrease below IC. If it will decrease below IC, what will happen? TIR will not happen, and this optical fiber will stop working, right? So that means this I should have what? Some maximum value. So it can't decrease, it can't be, I can't be less than IC. If it can't be less than IC, that means you can't increase theta naught beyond the limit, right? That, what does that mean? That this theta naught can't be increased beyond a limit, beyond a maximum value. That means for optical fiber to work, what we should have? For optical fiber to work, this theta naught must have a maximum value. Must have a maximum value. That means, and this maximum value is called acceptance angle. It's called what? That is called acceptance angle. Got it? Now, how to calculate this acceptance angle? This is the maximum value theta naught. And for theta naught equal to theta maximum, let me write it as acceptance angle theta naught maximum. What is I? I will be equal to IC. If we will increase this theta naught above this theta naught maximum, I will decrease, I will become less than IC. Got it? So that means that theta naught equal to theta naught maximum, I is equal to IC. And when I is equal to IC, can you tell me what is the value of sine I? That will become sine IC. And sine IC in this figure, you can see sine IC is equal to 1 by mu. We already know, right? So, but refractive 1 by mu is the refractive index of which medium? Denser medium with respect to rarer medium. So that is here N2 and it is here N3. That means sine IC equal to refractive index 1 by refractive index of denser with respect to rarer. That is 1 by refractive index of medium 2 with respect to medium 3. Right? Or I can write this as refractive index of 3 with respect to 2, or I can write it as N3 by N2 simply. So that is the value of sine I we got. Now you need to find the value of theta naught. So you can you can keep the value of sine I in this expression and you can get the value of theta naught. Let me write this as equation 1 and this one as equation 2. So if sine I is N3 by N2, and you can see in this expression, we are having cos I instead of sine I. So how will I find cos I? So this cos I will be equal to 1 minus sine square I. 1 minus sine square I or sine square IC. That will become 1 minus, let me write IC. So 1 minus sine square IC means N3 square divided by N2 square. That is cos square IC equal to, right? That means cos IC value you got, that is equals to N2 square minus N3 square divided by N2 square. So cos IC value you will get it as N2 square minus N3 square divided by N2. It will come out of the root. So you already know that at I equal to IC, theta naught equal to theta naught max, right? And you can keep these values in equation first, that sine theta naught equal to N2 cos I by N1. So you can get the value of sine theta naught equal to N2 by N1 cos I. Cos IC. Sine theta naught, if sine theta naught is theta naught maximum, that will become equal to N2 by N1, and cos IC value you have already evaluated, that is nothing but root over N2 square minus N3 square divided by N2. Now this N2 will be cancelled out and you are left with theta naught max equal to sine inverse root over N2 square minus N3 square divided by N1, and this N1 is out of the root and whole is in sines. That is the maximum value of theta naught, right? So they can ask you direct questions on that. In case here I have solved this for optical fiber, they may give a rod here and they may ask that for what value of theta naught this I can never be, this light ray is always undergoing TIR. So that maximum value of theta naught is nothing but this one. Got it?